Today, we are diving deep into something that feels like science fiction, but it's happening right now: computer vision. We're going to pull back the curtain and see exactly how we teach a machine to see and understand the world, almost like a person does.
So let's just jump right in with the big question. How does a computer actually learn to see? I mean, when you show your phone a picture, what is it really looking at? How does it go from just a file to recognizing your face, or a car, or even a handwritten note?
Well, here's the first thing you have to wrap your head around. A computer doesn't see a beautiful photograph of a sunset. Not at all. It sees a massive, and I mean massive, grid of numbers. Each number just represents the brightness of a single tiny dot, a pixel. That's it. That's the huge gap we have to bridge.
Now you might be thinking, okay, numbers. Why not just feed all those numbers into an AI? Well, here's the problem. Even a teeny tiny 28 by 28 pixel image, that's 784 separate numbers. For a standard AI, that is way too much to handle efficiently. But more importantly, just feeding it a long list of numbers loses all the crucial context, like which pixels are next to each other to form a line or a curve.
So that fire hose approach isn't going to work. We need a much smarter way to do this. We have to help the AI zero in on what actually matters in that giant sea of pixels. So how on earth do we do that?
Well, this brings us to our first amazing tool in the toolbox. It's a process called image convolution. The best way to think about it is like sliding a little magnifying glass over the image. But this isn't just any magnifying glass. It's a special filter designed to hunt for specific things, like the sharp edge of a box, the gentle curve of a circle, or different textures.
So here's the play-by-play. You take this little filter, also called a kernel, and you place it over one small patch of the image. You multiply the pixel values by the numbers in the filter, and then you just add all those results up to get one single new pixel. Then you just slide the filter over to the next spot and do it all over again and again and again across the entire image. And here is where the magic happens. By choosing the numbers in that filter very carefully, you can make it a feature detector. So, for example, you can design a filter that only gives you a high number when a pixel is really different from its neighbors. And what does that mean? It means you've just found an edge. And boom, look at this. On the left, you've got that messy grid of raw pixels. But after you run a convolution filter over it, look what you get on the right. All the noise is stripped away, and we're left with a clean, simple map of just the important features. In this case, the edges of the shape. It's night and day.
Okay, this is awesome. We've managed to find the important stuff. But, we still have a lot of data to deal with. So the next logical question is, how do we make this new feature map even simpler and more manageable for the AI?
And that brings us to our second key concept for today: pooling. This is a brilliant trick for shrinking the feature map we just made. It's all about making the system faster and more efficient. And the most popular way to do it is with something called max pooling. And you're going to love how simple this is. You just take your feature map and you chop it up into little squares, maybe 2 by 2 pixels each. Then, for each square, you look at all the values, and you just keep the biggest one, the maximum value. That's it. You throw the rest away. The result is a much smaller map that still captures the strongest signals of the features we found. All right, let's pause for a second. We've got our two main building blocks. We have convolution to find all the important features, and we have pooling to simplify and shrink everything down. Now, we're ready to put it all together. And when we combine these two powerhouse techniques, we create something truly special: the convolutional neural network, or CNN. You can think of this as the AI's visual brain. It's the whole architecture that puts these pieces to work to understand complex images.
So the whole thing works kind of like an assembly line. The image comes in, it goes through a convolution layer to find some features, then a pooling layer to shrink it down, and we often repeat that process multiple times. This allows the network to learn simple things first, like edges, and then combine them to understand more complex things, like eyes or a nose. At the very end, the final simplified map is flattened into a single list and fed to a regular neural network, which makes the final call, saying, yep, that's a cat.
Okay, so that's the theory. It sounds pretty cool, right? But does it actually work in the real world? Let's take a look at a classic example that really shows off the power of a CNN. The task is a famous challenge in machine learning, teaching an AI to recognize messy human handwriting, specifically digits from 0 to 9. We give the AI a massive database of these handwritten numbers, and its job is to figure out how to tell them apart.
So for this specific job, we build a custom CNN. Its first layers of convolution are trained to spot the basic building blocks of numbers. You know, the little strokes and curves. Then the pooling layers simplify those feature maps. And at the very end, the output layer has 10 possible answers, one for each digit, and it makes its final prediction.
And here is the absolutely crucial part. The network isn't just memorizing what a 7 looks like. It's actually learning, layer by layer, in a hierarchy. It learns what simple lines are, then it learns how those lines combine to make the shape of a 7 versus a 1. It's building a genuine understanding from the ground up.
So, the moment of truth. How well does it actually do? After all that training, the model achieves a mind-blowing 98.8% accuracy. But wait, because here's what makes that number truly incredible. That accuracy rate, that was on 10,000 handwritten digits that the AI had never seen before. This is huge. It means the AI didn't just memorize the training pictures, it learned the concept of each number well enough to recognize it in a brand new context. That is the true test of intelligence.
Which brings us to our final thought. Using these building blocks of convolution and pooling, we've taught a machine to read our own messy handwriting with almost perfect accuracy. So if an AI can master this today, it really makes you wonder, what will it learn to see tomorrow?